Now, when we say that acids produce H plus ions, again, which is a proton in solution, recognize that a bare proton in water in particular is not going to be able to just sit around. It is going to attach to something, and because it's so positive. And what ends up happening is water, H2O, generally has some extra electrons, some unpaired electrons. They're not extra, but they're unpaired electrons sitting on that oxygen. Because they're sitting there, they're negative, they're electrons. They very much draw in that proton. So what ends up happening is if you have an acid in water that's giving off H pluses, those H pluses will attach to H2O and form H3O plus. And this is the complex that forms in water, and it's known as the hydronium ion. And anytime you hear me mentioning hydrogen ions, protons, or H3Os in reference to acids, it's really all the same thing, because when I talk about the number of H pluses, they're all going to, in water, they're going to all attach to these H2Os and make H3Os. So the number of H pluses or H3Os is the same. So you'll see chemists going back and forth when they talk about the hydronium ion or the H plus concentration in solution. It really is kind of the same thing. So to more accurately portray what's the Bronsted-Lowry theory, the hydronium ion is used instead of the hydrogen ion, because you're showing that the water has accepted that proton from whatever your acid is. Now, amphoteric is a phrase that means something that can behave as either an acid or a base, so it means it can either give an H or accept an H. Water is the most common example. It can either become H3O plus, which means it's accepted a proton and acted as a base, or it can give up one of those H's and become OH minus, in which case it's acting as an acid because it's giving up that H plus. Now, whenever this happens, this acid-base thing with the Bronsted-Lowry, you get what's known as a conjugate acid or a conjugate base. What happens, basically, if you have a reversible reaction and you have an acid, it's going to release the H. Well, what's left, if it comes backwards, is now going to accept the H back. So whatever starches your acid becomes your conjugate base, and of course whatever starches your base becomes your conjugate acid. And I think this will make a little more sense when you look at an actual example. In this example, I have NH3 and H2O. Going forward, the H2O, or the H2O, is going to give one of its H's to the NH3. So this is acting as an acid because it's a proton donor. It's giving up the H+, and the NH3 is accepting it, so it's a proton acceptor, so it's acting as a base. Now, once this acid gives up its H, what's left is OH minus. So if we come backwards, going forward it gave up an H to turn into OH. If we come back, it's going to accept that H back, so it acts as an acid going forward, but what's left will act as a base coming back, so we call that the conjugate base. So what's left of your acid always becomes your conjugate base. And in the case of the ammonia, over here going forward, it's going from NH3 to NH4, so it's accepting an H, so it's behaving as a base. Well, in my reverse reaction then, if we go backwards, it's going to have to give that H back, so it'll behave as an acid. So what's starting out as my base, coming backwards, will behave as my conjugate acid. So just recognize, with a Bronsted-Lowry, if you give up a proton, you're behaving as an acid. If you accept the proton, you're behaving as a base. But whatever's left will be the conjugate opposite of what you start with. Whatever starches your acid, what's left of it will become your conjugate base on the right side. Whatever starches your base will become your conjugate acid on the other side as well. So it goes back and forth. Now here's an example where water is behaving as a base. In this case, HCl, as you know, is an acid, so it's going to donate an H to the water. So what's going to happen is the water will turn into H3O. So the HCl is an acid, it's hydrochloric acid, so what's left of it over here will be my conjugate base. The water is going from H2O to H3O, so if we go forward here, it's accepting the proton over here, so on the left side it's behaving as a base. What's left of it on the right side, of course coming backwards, would be my conjugate acid. Notice, by the way, the water here is donating a proton, here it's accepting it, so it's behaving as an acid or a base, so again, it is amphoteric, it can do either one. A minor point that you don't really have to focus on a whole lot, if you have a strong acid going forward, HCl is a strong acid. It gives up this H. it's not going to want to take it back. So generally what we say is if it's a strong acid going forward, the conjugate will be very weak. So a strong acid will have a weak conjugate base, and a strong base will have a weak conjugate acid. And again, strong acids are simply things that completely dissociate. Like HCl will completely break apart. Nitric acid will completely break apart. You can have, and sodium hydroxide, by the way, is a strong base. It will completely break apart into Na ions and OH ions. You can have weak acids and weak bases that only partially break apart. They don't go all the way over here. You don't lose all the H pluses. Some of these will break apart in the H plus, but some will not break apart. Some of these will break apart in the NH4 and OH, but many will not. So they are considered to be weak acids and weak bases. Not going to review naming a whole lot. We've been through that before. 8 becomes ic acid, it becomes us acid, and we've been through all these rules before, so I'm hoping they are fairly comfortable, or you're comfortable or familiar, or they seem kind of familiar to you. If you need to, you can slow down and look over those rules in this video. And here's what I really want to get to now. This is the self-ionization of water and pH. And what is pH and where does it come to? Or where does it come from, I should say. Turns out that if you have just neutral water, occasionally one water will hit another and transfer an H to the other one. So what will happen is this will give one of its H's over here, so I'll have H3O and OH. Notice that it comes from two waters. You always get one H3O and one OH. So you get one acid ion, the hydronium ion, and you get one hydroxide, the base ion. In pure water, both the hydronium and hydroxide ions are found in concentrations of 1 times 10 to the minus 7. That is 0.6 zeros and a 1, 0.000001 molar. Very, very dilute. Because they're at equilibrium, and you don't include liquid water in the equilibrium expression, KEQ or K water can be expressed as the following. And you don't need to reference all this. I'm just giving you some background there, and we don't really need to get into that. But just recognize that the formula for the dissociation of this stuff here is the KW, which is equal to my H3O concentration times my OH. So even if you're not totally sure what the heck am I talking about here, recognize that in a neutral solution, the concentration of H3O is going to be 1 times 10 to the minus 7. The concentration of the OH is always 1 times 10 to the minus 7. The product of them is called the KW, and that KW, it turns out, is always 1 times 10 to the minus 14. So just recognize that the H3O times the OH, and this is the one main thing I want you to get out of this, the H3O times the OH is always 1 times 10 to the minus 14. Now in a neutral solution, these are both the same, so that's why it's neutral. So the concentration of your H3O is equal to your OH concentration. Now, what if they aren't equal? So using the KW, if the concentration of H3O is 4 times 10 to the minus 8, what's the OH? Is this acid, base, or neutral? Okay, well, we know that the product of the H3O and OH is always that 1 times 10 to the minus 14. They're giving me the H3O. So now I can just simply solve for this one. Now the numbers are kind of weird. You got 1 times 10 to the and all this sort of thing. But all you're doing here is you're saying, well, how many OHs do I have? So I'm going to divide both sides by 4 times 10 to the minus 8. That cancels on the right side. So on the left side, I take 1 times 10 to the minus 14 divided by 4 times 10 to the minus 8, and I get 2.5 times 10 to the minus 7. Now the question, is it acid, base, or neutral? Which do you have more of? Do you have more OH or do you have more H3O? Well, 4 times 10 to the minus 8 is 0.7 zeros and a 4. 2.5 times 10 to the minus 7 is 0.6 zeros and a 2.5. So this is a larger number than this is. So what that means is I have slightly more OH than I do H3O. So this is a slightly basic solution. Now I'm hoping you're roughly familiar with the pH scale, which I'll talk about down here a little bit. pH, which you may remember, if you're at 7, you are neutral. If you're below 7, you're acidic. If you're from 7 up to 14, you're basic. Now, before I talk a little bit about what pH is and how we calculate it, let me remind you very briefly what is going on with logs. A log of a base 10 is what would I raise 10 to get a particular number. So 10,000 is the same as 1 times 10 to the 4th. So what would I raise 10 to get 10,000? It's 4. So the log of 10,000 is 4 because I would raise 10 to the fourth power to get 10,000. What if I had 0.001? Well, that's 1 times 10 to the minus 3, or 10 to the minus 3. So what would I raise 10 to get this number? It's negative 3. So that's where log comes from. And we'll do a little bit of that briefly, but just make sure you know where the log button is on your calculator if you forget some of that. Again, the pH scale 7 is neutral. That would be pure water. Above that, if we're going down in terms of like towards 0, of course, you're going to become more acidic. And as you go above that, you're going to become more basic. Now, what is pH? Where does it come from? pH, and again, it is the negative log of the H3O concentration. I don't want you to get too hung up on this or too lost in it, but just recognize what we're going to do is take the, just find on your calculator the log button. If you have the H3O concentration, you just take the log of it. The negative means you're going to get rid of the negative sign that's there, and then that's your pH. And I'll just show you an example. I'm just trying at this point to give you a feel for it. Now remember, the H3O times the OH is always 1 times 10 to the minus 14. And because of that, it turns out, and I'll show you this why this works in a minute, the pH plus your POH actually always adds up to 14. Okay, now let me show you what this means and what I mean by pH and POH. The H3O times the OH always has to equal 1 times 10 to the minus 14. So if you look at this as an example, 1 times 10 to the minus 13 times 1 times 10 to the minus 1 adds or multiplies out to 1 times 10 to the minus 14. Notice what's happening, that as my H3O concentration gets higher, okay, so I'm going from look at all these zeros, and a 1 down to 0.1. I'm getting more H3O. Look at what's happening to my OH. It's going from very concentrated getting lower. So as one of these goes up, the other goes down. Well, remember what I just said about what's pH, which would be the negative log of this number, and POH, which is the negative log of this number. It's basically what would I raise 10 to get this number, and I get rid of the negative sign. So this has raised this. What do you raise 10 to get negative 13? It's negative 13 here, obviously. Get rid of the negative, it's 13. So the pH here is 13. So notice what's happening, that as I go, the pH, which is the negative log of the number, which is really the exponent here, goes from 14 to 13 to 12. What is happening to my H3O concentration? It's getting higher. So notice that as my pH gets lower, my H3O gets higher, which is why we say it's becoming more acidic. Notice the OH, which is the complete opposite. The POH is the negative log of the OH concentration. So again, if this is my H3O, this is my OH. What would I raise 1 times 10 to the minus 3 to get, 0.01? It's minus 3. Get rid of the negative, you got a 3. So notice the pH here is 11. The POH here is 3. They add up to 14. But again, what the key, and you don't have to do a lot with the POH, but just recognize that if you take the negative log of the OH and the negative log of the H3O and add them, you're always going to get 14. And again, notice these move opposite of one another. It's the H3O goes up, the OH goes down, and vice versa. But the pH, which is the most common scale and is the one you're most familiar with, really focuses on this H3O concentration. Notice what I have here with this chart, that as the OH concentration decreases, my H3O or my H plus or H3O concentration increases, and when they are at the same spot, it's 7, they are neutral, and that's where this is 7 and this is 7, they add up to 14, and this are identical.